Okay, if we look across the room at the boards, everybody has the same correct answer. We know the Kb for morphine, so we find the Ka for the conjugate acid. As we start working on this, you want to get familiar with the nomenclature too. The amines end in ine, ene or ein, depending how we pronounce it. And then when we think about the conjugate acid that has that one extra proton, it's eum. So this is the morphinium ion, is the conjugate acid of the weak base morphine. So we know Ka is Kw over Kb. 1 times 10 to the negative 14th divided by Kb, 7.5 times 10 to the negative 7th, gives us 1.3 times 10 to the negative 8th is equal to our Ka. So again, comparing these, for morphine, which is going to be more pH active, morphinium or morphine? Morphine, because it has the bigger K value, negative 7 versus negative 8. It's not quite as big a difference as the other one was. Okay, so that was an introduction to these conjugates. Now let's look at the application of this. In application, we talk about the acid-base character of salt solutions. You remember from your high school chemistry that when you titrate, acid plus base yields salt plus water. And we always think of at the end of titration that something is neutral, right? But it's really not neutral pH 7 all the time. Because when you titrate an acid and a base, you make a salt, and if that salt contains ions that have no pH effect, then the solution will be neutral. But if you produce a salt whose ions are conjugate bases of weak acids or conjugate acids of weak bases, then you can have a different pH than 7 and your solution won't be neutral. And that's where all this equilibrium stuff comes in that's going to get messier. Same math, harder chemistry. So, we may have some acid-base behavior. So, how do you tell? You look at the formula for the salt and identify the two ions. Then you identify the ions as either conjugates of weak acids or bases, and if so, then they will have pH effect. Conjugate bases of strong acids do not affect the pH. So you decide, do I have an acid, do I have a base, or both? If you have both, an acid and a base, then you decide which is stronger. And we kind of practiced that a little looking at the K values, and that will tell you if it'll be acidic or basic. For our purposes in this class, we will assume that metal ions have no pH activity. Okay? So for this class, if it's a metal, it has no pH activity. Now, some metals do have pH activity. Aluminum is one of them. So because aluminum does have pH activity, we're not using it. Most of the metals will be the alkali metals. And alkali metals have no pH activity, so they don't have to worry about what's going on. Okay, so we looked at some examples of those conjugate bases of weak acids acting as bases. Conjugate acids of weak bases can act like acids because they are. So let's look at the example of the ammonium ion. Ammonia, NH3, is a weak base. Ammonium is its conjugate acid. So the ammonium ion can go into equilibrium with ammonia and a hydrogen ion. So we can look at this and say, okay, I'll find the Ka for ammonium. That's equal to Kw divided by the Kb for ammonia. So we look at our chart of Kw at different temperatures. That was earlier in the chapter in your note packet. Kw is 1 times 10 to the negative 14th. Then we look up the Kb for ammonia on the Kb chart that's a couple pages back in the packet. 1.8 times 10 to the negative 5th. And we get our Ka for ammonium is equal to 5.6 times 10 to the negative 10th. So now we have a Ka for this cation that is a conjugate acid of a weak base, or a protonated base, or a pH-active cation. It can be called a lot of different things. Now we can use this information to determine the pH of salt solutions. So let's look at a typical problem. What's the pH of 0.1 molar ammonium chloride solution? This is where you have to start thinking, what's in my beaker? And we are going to practice what's in my beaker over and over till you're sick of it. So you have to be able to look at the formula, ammonium chloride, and say, okay, this is an ionic compound. When I put it in water, it breaks completely into its ions, ammonium ion and chloride ion. Now we have to evaluate those ions in terms of acid-base behavior. So the ammonium ion is the conjugate acid of a weak base, and the chloride ion is the conjugate base of a strong acid. So we have to be able to look at those things and decide what they are in terms of pH activity. The conjugate base of a strong acid has no interest in picking up a proton. Strong acids dissociate completely. Chloride doesn't want a proton, so it has no pH activity. The conjugate acid of a weak base will act like an acid. And that means that it's now going to act like a weak acid, so I'm going to have to figure out what the pH is by using an ice chart, finding the hydrogen ion concentration, and then determining pH. And because it's acting like an acid, I need a Ka. And I have to find that Ka from the Kb. So now we set up our ice chart, we find Ka from Kb, and we just did that up here. Okay, we just did that. So the Ka for the ammonium ion is equal to 5.6 times 10 to the negative 10th. Now this becomes same old, boring math ice chart that we've been doing since chapter 15. But we had to figure out what goes in the ice chart, and you have to know what's in my beaker. Because for many of you, if you're at all like my previous students for the past few years, if we just said ammonium, that might make you think of ammonia. It would make you think it's basic, and it's not. It's acidic because it's ammonium. So we have the ammonium ion in equilibrium with ammonia plus hydrogen. There's no chloride in here. How come there's no chloride in here? Because it doesn't do anything, right? It's just hanging out. It's a spectator ion. Okay? So now, what is my concentration of ammonium ion? Well, I know that we had 0.1 molar ammonium chloride. There is one ammonium ion in one ammonium chloride. So if this is 0.1 molar of the compound, I have 0.1 molar of the ion. Will it sometimes be different? Yes. If you had something where there were two of that ion, then it would be double the concentration. So now we set up our ice chart. 0.1 molar. This is now the same as every other problem we've done for the last 3 weeks. 0 and 0. Minus x, and plus x. 0.1 minus x, and x. Now we know Ka because we calculated this previously. So now we can determine what the concentration of the hydrogen ion is at equilibrium, and then we can find the pH. So we know Ka. We know Ka is equal to the ammonia concentration times the hydrogen concentration divided by the ammonium concentration. So we can plug our numbers in. 5.6 times 10 to the negative 10th is equal to x times x divided by 0.1. Because K is 5.6 times 10 to the negative 10th, it's safe to assume X is small. So when we multiply, we get 5.6 times 10 to the negative 11th is equal to X squared. Now in this problem, X is representing for us the hydrogen ion concentration. So that is equal to the square root of 5.6 times 10 to the negative 11th. So my hydrogen concentration is equal to 7.5 times 10 to the negative 6th molar. Now if I know the hydrogen ion concentration, from this I can find the pH. So the pH is minus the log of 7.5 times 10 to the negative 6th. The pH is 5.13. Now, as always, we ask ourselves, is this a reasonable answer? And the answer is yes, because it's less than 7, it's acidic, and we would expect it to be acidic because the ammonium ion is an acid. So are you feeling bored yet with the math? Good. But then you see how it's harder to figure out what's going on in the beaker. That's the tricky part now. Okay, go ahead and do the one on the next page on your whiteboards.